let's consider a man standing on a bathroom scale in an elevator. We want to know, what does the scale read if we're accelerating upwards at a given acceleration, or if we're moving upwards at a constant speed. So obviously, if we're standing on the scale, it should read correctly if we're just standing there outside of an elevator. But inside of an elevator, what's going on? Well, we'll start and try and follow our problem solving where we read and we note some things we know. Our mass of the person is 75 kilograms. And the acceleration, for part A at least, is 1.2 meters per second squared upward. We'll now draw a little sketch of the situation to understand what's going on. We have an elevator, and inside of the elevator, we have a scale here, and then we have a man standing on the scale, and there's an interaction here between the man and the scale. Third, we'll see, what do we draw a free body diagram of? We could draw a free body diagram of the scale, but then we'd have to worry about the interaction of the scale with the elevator, which I don't care about. It makes more sense to me to draw a free body diagram of the man. So we'll draw a free body diagram of the man. And we'll draw the body. We'll have a coordinate system. We'll call y positive going up. And then we'll apply the forces that are acting on the man. This man will have weight acting down. That's equal to mass times gravity. And it will have some normal force, some interaction with the scale that's keeping him from passing through the scale. So this we'll call the force of the scale. And that force that's exerted on the scale is what the scale uses to give a reading. So the reading of the scale will be based on that force. So this is the force of the scale acting on the man. By Newton's third law, the force of the scale acting on the man is equal and opposite to the force of the man acting on the scale, which is what causes the scale to have a reading. And sometimes I find it useful to explicitly say that here are the sums of the forces, and that's going to equal mass times acceleration. So here's my effective forces. The man is accelerating upwards with mass times acceleration. So now we will move on to considering Newton's laws, Newton's second law specifically, and we'll say that the sums of the forces are equal to mass times acceleration. Let's go ahead and look at the y component. Call up positive, sum our forces in the y direction are equal to mass times acceleration in the y. I know this might seem like a lot of unnecessary writing, but I'm trying to give you tools for when you're considering more complicated problems of how to apply those. So going up, we have force of the scale on the man minus the weight of the man has to equal mass times acceleration. And since we've called that A, just A, I'll call it A here. We want to know the force exerted on the scale, because that's what's going to give us our reading. So we say the force of the scale is equal to, well, we add the mass times gravity to both sides. So this will be mass times gravity plus mass times acceleration. And if you want, you can even factor that out and call this mass times gravity plus acceleration. We can plug in the things we know. Looks like this will be 75 kilograms times 9.8 meters per second squared plus the acceleration of 1.2 meters per second squared. And when you evaluate that, it looks like we end up with a value of 825 newtons. So the force that's being exerted on the scale is 825 newtons. If the scale is a scale that reads in newtons, then this is what it will read. It will read 825 newtons. Now it's more common that your scales are going to give you a mass in grams or kilograms. So what would it read there? Well, it would be doing the conversion, assuming that you weren't accelerating, and saying that it would read a mass, an effective mass, of whatever the actual force applied on it is divided by gravity. And when you do that here, you end up with a mass of 84.2 kilograms. So if your scale is indeed reading in kilograms, then it would read 84.2 kilograms. That's higher than 75 kilograms. And why is that? Well, it's because we're accelerating upwards. So we're being forced downward into the scale. You can think about it like that, or the scale is forcing itself up into us. So the interaction between us and the scale is more than it would be normally. Lovely. All right, what about part B? Well, if the elevator moves upward at a constant speed, then at a constant speed, our acceleration is equal to 0. So if we have an acceleration equal to 0, whatever our velocity is here, 1 meter per second upward, we can go back. Our analysis should still be valid. It's just now we know acceleration is 0. So I can use my results from over there and say, well, the force on the scale is equal to mass times gravity plus acceleration, just what I got over here. But now I can say that acceleration, since I'm moving at a constant speed, is 0. So my force ends up just being mass times gravity, which gives us 735 newtons, or using the same force over gravity as we used previously, this would give us the 75 kilograms coming back out, which is what you would expect, that if you're standing on there and there's no acceleration, then it reads normally. So while you're going upwards, accelerating upwards, it reads higher. While you're traveling normally, it reads the same as it would normally. And then as you slow down, as you reach that top floor, it will have a negative acceleration. And so you'll feel a little bit lighter as that happens. You won't be pushing down on the scale as much, and you'll actually have a little bit less weight registered on the scale as you're decelerating at the top.